There is a feature built into every modern commercial aircraft that almost no one in the passenger cabin knows exists. The engines, each one weighing between 3 and 8 metric tons, producing tens of thousands of pounds of thrust and representing several $1 million of hardware, are deliberately designed to separate from the aircraft under specific impact conditions. Not to fall off randomly, not because the attachment failed, but because the engineering specification requires it. The fuse points that allow this separation are calculated, tested, and certified as a safety system. The engine is supposed to come off. And once you understand why, the logic is not just defensible, it's the only rational design choice available. To understand the reasoning, you need to understand what a jet engine contains and what it does to an airframe if it stays attached during a crash sequence. A turbofan engine is a rotating pressure vessel operating at extreme temperatures. The fan at the front spins at several thousand RPM. The compressor stages behind it spin faster. The turbine at the rear, which extracts energy from the combustion gases, operates at temperatures exceeding 1,400 degrees Celsius in the high-pressure stages. The engine contains a continuous supply of jet fuel being actively burned. It is connected to the aircraft's fuel system through lines carrying fuel under pressure. In a severe impact, a runway overrun, a gear collapse, a hard landing that damages the structure, the engine and its pylon experience loads that far exceed normal operating limits. If the engine is rigidly and permanently attached to the wing structure at that moment, several things happen in sequence, and none of them are survivable. The first problem is structural. A 3 to 8 metric ton mass attached rigidly to a wing, subjected to sudden deceleration forces from a crash impact, becomes an enormous lever. The pylon transmits those forces directly into the wing box, the primary structural element of the wing. Wing boxes on commercial aircraft are not designed to absorb crash energy through deformation the way automotive crumple zones are. They are optimized for flight loads, lift, bending, torsion. A severe transient impact load transmitted through a rigidly attached engine can fracture the wing box, collapse the wing structure, and compromise the integrity of the fuselage at the wing attachment points. The aircraft breaks apart at the wrong place, not at a controlled separation point, but through uncontrolled structural failure that propagates into the cabin. The second problem is fuel. The wing is a fuel tank. On a fully loaded wide-body aircraft, the wings may contain 50,000 to over 200,000 liters of jet fuel distributed across multiple sealed wing bays. The engine pylon passes through or adjacent to the wing structure, and fuel lines run from the wing tanks through the pylon to the engine. If a rigidly attached engine tears the wing structure during a crash, it opens the fuel system. Jet fuel at that temperature and pressure, exposed to an engine that is still hot and potentially still partially running at the moment of impact, produces a fire. Not immediately and not always, but the probability is high enough that aircraft fire investigation reports consistently identify fuel-fed post-crash fires as a primary cause of fatalities in otherwise survivable accidents. An accident that the occupants could survive mechanically, the structure held, the seats held, the restraint systems worked, becomes fatal because fuel ignited after impact. The fuse pin system addresses both problems simultaneously. The engine is attached to the pylon through a series of structural fittings, and those fittings include engineered weak points, fuse pins, that are designed to shear at a specific load threshold. Below that threshold, the attachment is as rigid and strong as any other structural joint on the aircraft. The engine stays on through turbulence, hard landings, engine surges, bird strikes, and every other operational load the aircraft normally encounters. The fuse pins are not fragile. They are rated to handle normal flight loads with significant margin. But when impact loads exceed that defined threshold, when the crash geometry produces forces on the pylon that would otherwise destroy the wing structure, the fuse pins fail first. They are the weakest point by design, in the same way a fuse in an electrical circuit is the weakest point by design. The engine separates cleanly at the pylon attachment rather than tearing the wing apart. The separation geometry is also deliberate. The fuse pin arrangement is designed so that when the engine does release, it moves forward and downward, away from the fuselage, away from the cabin, and away from the fuel-laden wing structure. It does not rotate upward into the wing. It does not swing inward toward the fuselage. The kinematics of the separation are controlled by the geometry of the attachment fittings and the direction of the impact loads. When it works correctly, the engine leaves the aircraft without rupturing the main fuel lines in the wing, without breaching the wing box, and without contacting the fuselage. The fuel system seals itself at the separation point through check valves that close when flow reverses, another engineered response to the same failure scenario. The wing structure, relieved of the engine's mass and its associated impact loads, has a better chance of remaining intact. The cabin survives. The fuel stays contained. There are documented cases where this system performed exactly as designed and where the outcome difference was measurable. The 1989 Sioux City DC-10 accident, where an uncontained engine failure destroyed all three hydraulic systems, resulted in a crash landing in which the aircraft broke apart, but the engines separated during the sequence, and the fire, while present, did not immediately engulf the survivable sections of the fuselage. More directly relevant is the analysis of accidents where engine separation did not occur as intended, or where the impact sequence caused an engine to rotate into the wing rather than away from it. In those cases, fuel-fed fire was a consistent outcome. The engineering case for the fuse pin system is built substantially on that evidence. The system has limits, and understanding them clarifies what the design is actually solving for. The fuse pins are calibrated for a specific load range. An extremely high energy impact, a high-speed controlled flight into terrain, a catastrophic structural failure at altitude, produces forces that are orders of magnitude beyond what the fuse pin geometry can manage in a controlled way. In those scenarios, the aircraft is not in a survivable accident sequence, regardless of whether the engine separates cleanly. The fuse pin system is not designed to save the aircraft in every conceivable crash. It is designed to convert a subset of otherwise unsurvivable accidents, severe but low-speed ground impacts, into survivable ones by preventing post-crash fire from secondary structural failure. That is a specific, bounded problem, and the engineering solution is calibrated to it precisely. Military fast jets use a conceptually related but mechanically different solution: the ejection seat. The crew leaves the aircraft before or during the crash sequence. The aircraft is expendable. Commercial aviation cannot use that approach. The passenger cabin cannot be evacuated in flight in a crash scenario. The only available strategy is to manage the crash sequence itself, controlling how the aircraft brakes, where energy is absorbed, and what secondary events are prevented. Fuse pin engine separation is one element of that strategy. Fuselage underfloor structure designed to absorb vertical impact loads is another. Seat track attachment points engineered to fail at controlled loads before the seat fails are another. Every one of those design features reflects the same underlying logic. If the crash is going to happen, engineer the sequence so that the structure fails in ways that protect the occupied volume rather than ways that destroy it. The engine falling off is not the aircraft failing. It is the aircraft working. The distinction matters because it reflects a design philosophy that runs through every certified transport aircraft flying today. The recognition that safety engineering is not only about preventing accidents, but about ensuring that when accidents occur, they occur in ways that people can survive. That requires accepting that certain components will be destroyed, and designing precisely which components those are and in what sequence they fail. The fuse pin is a small piece of metal. What it represents is the conclusion of a detailed analysis of how energy moves through an airframe during impact and where that energy can be redirected away from the people inside. That analysis, applied consistently across decades of accident investigation and design iteration, is why commercial aviation's survivability record in accidents that do occur is as high as it is.